Okay, so it is the first day of actual lecture on chapter 4. No one's called in, so I'm going to take this hour and just start doing sample problems from the chapter. So I'm going to change my share screen to some of the problems. So chapter 4 deals a lot with stoichiometry, which is the relationship between amounts of reactants and products. And when I say amounts, that usually means moles, but it also deals with masses of products and reactants. So when we look at a balanced reaction, as we see here, the coefficient for aluminum hydroxide is 1. The coefficient for hydrochloric acid is 3. The coefficient for aluminum chloride is 1. And the coefficient for H2O is 3. So if we don't have a coefficient written, the default coefficient is 1. So what do these coefficients mean? Well, unfortunately, in this reaction, you could assume that that's 1 gram plus 3 grams gives you 1 gram plus 3 grams, and 4 grams gives you 4 grams. It works out. But it turns out that that's not the case. You would, in fact, not get 1 gram of aluminum hydroxide for 1 gram of aluminum chloride. And the simple reasoning is that for every hydroxide, which weighs, 16 or 17, you'd be replacing it with a chlorine that weighs twice as much. So if you started with 1 gram here, you would certainly get something like 1.5 grams here. And water molecules clearly weigh less than hydrochloric acid molecules, so this could not be 3 grams would get you 3 grams. It's just ridiculous. So what do the coefficients mean? They indicate that one of these formula units reacted with 3 of these molecules will give you 1 of these formula units and 3 of these molecules. Well, you'll notice if it's an ionic compound, I call it a formula unit. And if it's a molecule, I call it or if it's a molecular, I call it a molecule. And basically I'm looking for metal, non-metal is ionic, and all non-metals is molecule. So ionic compounds, formula unit, molecular compounds, molecule. So the coefficients mean 1 formula unit of this to 3 molecules of this gives you 1 formula unit of this and 3 molecules of this. That's all fine and well, but when you're doing chemical reactions, you're usually weighing things. You're not counting formula units or molecules. So when you're weighing things, what is more relevant is that you're probably weighing about 1 gram of material. So we've already been introduced to the idea of converting from moles to grams using molar mass. So these coefficients are used instead as 1 formula unit and 3 molecules. We say 1 mole of aluminum hydroxide. And that would be equal to 3 moles of HCl. Now, I'm not saying that these are equal, but rather I'm saying that if you use 1 mole of aluminum hydroxide, you will need 3 moles of hydrochloric acid. The equal sign helps me to use this as a conversion factor should I need to. So this is something I'm writing out right now for you to see, and it's something that you want to be able to do for any reaction that you see. And you should do that for every reaction you see immediately. So when should you stop? You should stop when you don't need to do this anymore. So how do you know you don't need to do this anymore? And the answer is simple. If you hesitate 1 little bit in writing this out, then you need to keep doing it. But if you can do this without hesitation, you're good to go. Okay, so here, this allows us to convert between moles of aluminum hydroxide and moles of HCl, or moles of aluminum hydroxide and moles of aluminum chloride, or moles of aluminum hydroxide and moles of H2O. Any pair of these I can convert between. So if we start off with 0.750 grams of aluminum hydroxide, as suggested above, and the question is, what's the mass of water produced, so this is our big goal, we can't go directly from grams of aluminum hydroxide to grams of water because these coefficients do not indicate grams. They indicate moles. So I can go from moles of aluminum hydroxide to moles of H2O. That I can do from the balanced reaction. So the next question is, can I go from grams of aluminum hydroxide to moles of aluminum hydroxide? And the answer is certainly. All I need is the molar mass of aluminum hydroxide. Can we go from moles of H2O to grams of H2O? Absolutely. All we need is the molar mass of H2O. And can we go from moles of aluminum hydroxide to moles of H2O? And the answer is absolutely. All we need is a balanced reaction. So a lot of this chapter is about going from grams of A to moles of A to moles of B to grams of B. In this case, A is aluminum hydroxide and B is H2O. So A just means something up here in the reaction, and B means something else in the reaction. Okay, so to do this, I'm going to scoot this sheet up a bit. To do this, we need the molar mass of H2O, and that's 18.02 grams. Now, the molar mass of aluminum hydroxide is 3 oxygens, that's 48. 3 hydrogens, that's 3.03, and 1 aluminum, which is 26.98. So I get 78.01. And of course, that means 1 mole is that many grams. So if we start off with 0.750 grams of aluminum hydroxide, oops, I already mapped it out. I don't want to map it out again, so I'm going to cross that out. So here, this is a conversion, this is a conversion, and this is a conversion. The first conversion, we need the molar mass of aluminum hydroxide. So here, I'm going to put the 78.01 grams on the bottom so that the grams cancel. And I'm going to put 1 mole of aluminum hydroxide on top. So this is the first conversion that matches that. Now I'm going to go from moles to moles, which means I use the balanced reaction. You see how I have this nicely written out? I know I want to end up with H2O, so I'm going to put 3 moles of H2O on top. And then I'm going to put 1 mole of aluminum hydroxide on the bottom. Next, we use the molar mass of H2O. And so I'm going to say that there are 18.02 grams of H2O to 1 mole of H2O. Now, we see in the balanced reaction, so I'm going to scoot this back down. We see in the balanced reaction there's 3 H2O, and students wonder, well, isn't that 18 grams for 3 moles of H2O? And the answer is no. 18.02 grams is 1 mole of H2O. How much would 3 moles weigh? 3 moles would be 3 times 18.02. So here we could do 3 times 18.02 grams of H2O over 3 mole of H2O, right? Because that's how much 3 moles of H2O weighs, 3 times 18. And you can see the 3's just cancel. So why don't we just do 1 mole? So it's important for these molar masses to understand you use the mass of 1 mole. So where do we take into account the fact that we get 3 for 1? Right here with the balanced reaction, right there. Okay, now we always like to estimate to see if we get the right answer or if we're using our calculator correctly. I would venture that 18 is close to 20 and 78 is close to what, 80? 20 goes into 84 times. So I have 3 divided by 4. Maybe a little tough to do, but 3/4 of 0.750 should be a little less than 0.750. So maybe it's, 0.6 or 0.5, somewhere in there. So that's what we should get for our answer. And we get 3 significant figures because here the coefficients are exact. They're defined by a balanced reaction where we make sure we have exactly the same number of atoms on each side. Okay, so let's see what we get here. 0.750 times 3 times 18.02 divided by 78.01. And I said it should be between like 0.5 and 0.6. We get 0.520 grams of H2O. And this is the type of work I would expect to see for a problem like this on an exam. Now, let me show you what I would not expect to see because it looks horrible. So here you can see we're not using any labels at all. So I don't know what weighs 1 mole or what 1 mole of weighs 78.0 grams. I don't know why you have 3 moles to 1 mole. Sounds like a great deal if you're getting the 3 mole out of it and giving up the 1 mole. This is horrible. And you would not even get passing credit for something like that. Okay, so that's the idea of stoichiometry, converting usually from grams to grams of one thing to another. Okay, oh, and I actually answered the second part, what mass of water in grams is produced. How would this change for what mass of HCl is required? Well, if we map it out, we would start with a 0.750 grams of aluminum hydroxide. We would want to end up with the grams of HCl. And what is the bridge between these two? The balanced reaction where we can go from moles of aluminum hydroxide to moles of HCl. Okay, so we've got the outline here. We know that the molar mass here is 78.01. I'm going to tell you that the molar mass of this is 36.46. And we can see that the ratio here is 1 to 3. Okay, so what you want to do now is pause this recording or pause this tape and see if you can solve this, and then turn it back on and watch me do it. And because you have already written out your solution, you'll be able to see me as I develop mine very quickly. So I'm not going to give much explanation. Okay, so hit pause. And you're back. Okay, so 0.750 grams of aluminum hydroxide times 1 mole of aluminum hydroxide per 78.01 grams of aluminum hydroxide. And I'm going to move my hand so you can look at this and compare it to what you've written. And then times 3 mole of HCl over 1 mole of aluminum hydroxide. And I'll move my hand so you can compare it to what you've written. And you can write then 36.46 grams of HCl to 1 mole of HCl. So again, for these molar masses, we don't care what the coefficients are up there. We just care what the formula is and what the mass is of one of those formula units, or 1 mole of that. Here, I would venture that 36 goes into 78 about 2 times. So 3 divided by 2 is 1.5. 1.5 times 0.750 puts us at about 1.1 or 1.2. So let's see what we get. 0.750 times 3 times 36.46 and divided by 78.01. And we get 1.05 grams of HCl. And this is the work I would expect to see. And there we go. Okay, so let's take a look at one more of these type of problems, and then we'll see how we can do more with this. So here's another one. The balanced equation for the reduction of iron ore to the metal is using carbon monoxide is as follows. So this is iron 3 oxide is what it's called. You react it with carbon monoxide and you get iron. And if you do this at a high enough temperature, this iron is actually a molten iron, and you pour it into something and it becomes solid iron. So what's really neat about this is that if you have this pure iron 3 oxide, the products you get are pure iron and carbon dioxide, and the carbon dioxide you can just release as gas and you've got pure iron. You don't need to purify this reaction to get your iron. It's great. Okay, now, what is the maximum mass of iron in grams that can be obtained from 454 grams of iron 3 oxide? So we're going to start with 454 grams of iron 3 oxide. And we want to know what is the mass of iron that we could form. So that's our goal. Now, what is the bridge between the grams of the iron 3 oxide and the grams of iron? The bridge is moles of iron 3 oxide and moles of iron. So what do we need for this first conversion to go from grams of iron 3 oxide to moles of iron 3 oxide? We need the molar mass. And the molar mass of this, if I remember right, iron is 55.85. Let me double check that. Yep, iron is 55.85. And oxygens are 16, so that's 48 total. So I didn't do that right. I get 159.70. And the molar mass of iron is 55.85. Now, what is the mole ratio here? 1 to 2. So we write our 454 grams of iron 3 oxide times 1 mole of iron 3 oxide over 159.70 grams of iron 3 oxide. And why am I putting the grams of iron 3 oxide on the bottom? So that the grams cancel. Now I want to cancel moles of iron 3 oxide. So from my balanced reaction, I'm going to put 1 mole of iron 3 oxide on the bottom, and I'm going to put 2 moles of iron on top. And then finally, I'm going to put 55.5 or 85 grams of iron on the top and 1 mole of iron on the bottom. Okay, so we can see we have 2 times 55.85, which is 110. 110 over 160 is approximately 2/3, and 2/3 of 454 is approximately 300. So 300-ish is going to be our answer. And let's see what we get. 454 times 2 times 55.85, and then divided by 159.70. And we get, and times 454. Oh, wait. I think I made a mistake because I did all that and I got 0.224. Let's try again. 454 times 2 times 55.85 and divided by 159.70. That's more like it, 318. 318 grams of iron. And so here's the work I would expect to see for that. Now, I do want to talk about this one phrase here. What is the maximum mass of iron that can be obtained? That maximum mass is given a term in chemistry. It's called the theoretical yield. So why do we have this term theoretical yield? Because there's another term, actual yield. So the maximum mass is your theoretical yield. Your actual yield accounts for loss. So maybe when you're pouring your iron out of this reaction, you spill a little and you don't get that. Theoretically, you could have, but you actually didn't. Sometimes the reaction does not go to completion, so you have some leftover iron 3 oxide. So maybe that's the reason your actual yield is less than it should be. Okay, so here you've got your theoretical yield versus your actual yield. Again, theoretical yield is the maximum you could get if everything went perfectly. And they also have something called percent yield. Percent yield is the ratio of actual yield to theoretical yield. And the way it looks is this. You take your actual yield, divide it by your theoretical yield, and times 100%. So if your actual yield is the theoretical yield, you have 100% yield. If your actual yield is half of the theoretical yield, your percent yield is 50%. Okay, so that would be A. What mass of carbon monoxide is required to react with 454 grams of iron 3 oxide? Okay, so for B, we want to know the grams of carbon monoxide. That's the question. And we're going to start with 454 grams of iron. So I want you to do this, map it out, and while you're doing it, so now that you see the problem here, I want you to hit pause and then hit play when you're done, so that when you're done, you can compare what I'm about to show you. Did you hit pause? You got to hit pause. Okay, and you're back. So we're going to convert this to moles of iron 3 oxide. We're going to convert that to moles of carbon monoxide, and then to grams of carbon monoxide. What do we need here? We need the molar mass of iron 3 oxide, which we already know is 159.70. We need the balanced reaction up here, which says we have, well, I got to move this down a little bit so we can see the balanced reaction. Where is that balanced reaction? That's a different reaction. Notice it's not carbon monoxide. So here we have carbon monoxide. So the balanced reaction, there's 3 carbon monoxides to 1 iron 3 oxide. And we need the molar mass of carbon monoxide. The molar mass of carbon monoxide is 28.01 grams. And here we need the balanced reaction. So you already have this written out, and you're just comparing what I'm writing to what you have written. So here we go. Doing my little estimating, 28 will go into that about 6 times. 3 divided by 6 is half. Half of that is like 220. So let's see what we get. 454 times 3 times 28.01 and divided by 159.70. is equal to 239. So you'll notice that in the work that I expect to see for these, I don't expect to see your calculation for molar mass. So you better make sure you get that correct. All right, and so that is this problem right here. Having trouble keeping track of the problems. So that's this problem right here. And if we take a look here and look at this reaction, let's take a look at one more thing about this reaction. So I'm going to push this on up here. So for this reaction, we have 454 grams here. For the carbon monoxide, we just calculated that it's 239 grams of carbon monoxide. And we found out that we would get how much iron? 318 grams of iron. So how many grams of carbon monoxide are produced? Well, we could do it this way. We could take our 454 grams of iron 3 oxide, convert that to moles of iron 3 oxide, convert that into moles of CO2, and convert that into grams of CO2. So we could do what we've been doing so far, or we could do this. The mass that you start with, the 454 and 239, should be equal to the mass that you end with, 318 plus however many grams of carbon dioxide you need to equal that mass when you add these two together. So let's see what this ends up being. 454 plus 239 minus 318. And I'm going to even estimate this because you add these two numbers together and you get really close to 700. 700 minus this, but not quite 700 minus this, is going to be almost 400. So I'm figuring the answer's got to be around 360, 370, somewhere around there. And we get that the grams of CO2 is 375 grams. Now let's see what answer we would have gotten if we did this reaction here, or this conversion. Okay, and 3 moles of CO2 to 1 mole of iron 3 oxide. And then the molar mass of CO2 is going to be 44.01 grams. So let's multiply these out. 454 times 3 times 44.01, and then divided by the 159.70. And we get 375 grams. So 2 ways to do that. But remember, this top way we could only do because we had the other 3 masses. Okay, so that's that problem. All right, now you can see that in this problem, it's just like the others except for one thing. You have to balance the reaction. Then you figure out what mass in grams is required to complete the reaction with 0.15 grams. So this is just like the other problems. Since you already have examples of this, we're going to skip this one. Okay, this one is a little bit different, so we're going to do this. Now here they're asking, what amount? If 6.2 moles of iron 3 oxide is used, what amount of carbon is needed and what amounts of iron and CO2 are produced? In this particular question, since they give you the amount in moles, they expect the amount to be in moles. So we want to go from 6.2 moles of iron 3 oxide to moles of, in this case, carbon. We also want to go to moles of iron. And we want to go to moles of carbon dioxide. Okay, so can we go directly from here to here using our balanced reaction? Or do we need to do that whole molar mass thing? And the answer is we can go directly. All we need is a balanced reaction. So if we take a look at moles of carbon, we start off with 6.2 moles of iron 3 oxide times, according to our balanced reaction, 3 moles of carbon to 2 moles of iron 3 oxide. And we will end up with moles of carbon. And you can see that this is 1.5 times that. So half of this is 3.1. So this is going to be 9.3 mole of carbon. And that's what I'd expect to see for a problem like that. 6.2 mole of iron 3 oxide times 4 mole of iron to 2 moles of iron 3 oxide. And here we have 2 times 6.2, which is going to be 12 mole of iron. And you might be wondering, so if this is 2 and that's 6.2, isn't it 12.4? And the answer is no, that's only 2 significant figures. And since we're using the multiplication rules, you only get 12 moles of iron, 2 significant figures. And lastly, for the moles of carbon monoxide, 6.2 moles of iron 2 oxide times 3 moles of carbon dioxide to 2 moles of iron 3 oxide. And here, when we look at the equation, 3 mole to 2 mole. So this is going to be the same answer as the one above, where it's going to be 9.3 moles of carbon dioxide. And that actually makes sense. If you start off with 9.3 moles here, you should end up with 9.3 moles here because the coefficients are the same. Okay, so this problem was a little bit different than the others, and I would actually say this problem was easier. We did not need molar masses. Okay. Put that over there. Now, this is something that we do want to cover. Ethane burns in oxygen. What are the products of the reaction? Write a balanced reaction. And what mass in O2 in grams is required for complete combustion of 13.6 grams of ethane? What is the total mass of products expected? Okay, so ethane burns in oxygen. Whenever you have what's called a hydrocarbon, hydrogen and carbon, hydrocarbon, and it reacts with oxygen, that's O2, your two products are always carbon dioxide and H2O. At room temperature, that would be carbon dioxide gas, and that would be O2, H2O liquid. Now, you may not know this, but I'm going to go ahead and tell you this. Ethane is a gas at room temperature. What is the state of oxygen at room temperature? It is also a gas. What are the two products again? Carbon dioxide and H2O. Okay, so let's balance this. It looks like we have 6 hydrogens here and 3 here. Now, I'm going to be honest. Normally, when you balance these reactions, you want to do it alphabetically. Carbon, hydrogen, and oxygen. So let's do this carbon first. 2 here, 1 here. We're going to put a 2 there. Now let's do the hydrogens. 6 here, 2 here. So I'm going to put a 3 there. And now we have a little bit of a problem because here we have 4 oxygens and here we have 3 for 7 oxygens. How am I going to get 7 oxygens when they come in pairs? Well, I'm going to do a 7/2. Because what's 7/2 times 2? 7. So I have my 7 oxygens. Now, we don't like balanced reactions that have halves as coefficients. So what do we do with this so that it's still balanced? We double all the coefficients. Okay, so get that written down. And after you get that written down, we're going to count and see if it is balanced when we double all the coefficients. So a little arrow with a 2 means double it. Okay, so let's check carbons. 2 times 2 are 4. 4 times 1, 4. 4 carbons on each side. Hydrogens, 2 times 6, there's 12 right there. 6 times 2, there's 12 right there. They match. Oxygens, 7 times 2 for 14 right there. 2 times 4 for 8, so we've got 8 right there. 6 times 1 for 6, so we've got 6 right there. 8 plus 6 is 14, which matches the other side. So this is your balanced reaction. Now, what mass of O2 in grams is required for the complete combustion of 13.6 grams of ethane? So there's our grams of ethane, and we want to end up with grams of O2. And what is the link between these two masses? Moles of ethane and moles of O2. So what is the molar mass of O2? That's easy, 32.00 grams. What's the mass of molar mass of ethane? Well, 2 carbons is 24.02, and 6 hydrogens is 6.06. So 24.02 plus 6 is going to be 30. And the 0.2 part and the 0.6 part comes to 0.8. And what does the balanced reaction tell us? It tells us that there are 7 moles of O2 and 2 moles of ethane. So the solution looks like this. 1 mole per 30.08 grams. Notice I'm using the labels. And I want mole of CH2 on the bottom, so I'm going to cross this out. And the reason I'm crossing that out is I don't want to get confused and borrow from this top one when I need the bottom one. And there's 7 mole of O2. And then there's 32 grams of O2 to 1 mole of O2. So let's estimate the answer. I would argue that 32 divided by 30 is about 1. 2 goes into 13.6 about 7 times. 7 times 7 is 49. So the answer should be around 50, we'll say. All right. How many significant figures do we get? We get 3. So 13.6 times 7 times 32 divided by 30.08 and divided by 2, we get 50.6 grams of O2. So for this problem, what are the things I would expect to see for A and B? So that's A and B. We are clearly showing the products and the balanced reaction. And this would be C, which is how many grams of O2. Now, D, what is the total mass of products expected from this combustion? Well, we know that from this, we've got 13.6 grams. And here we have 50.6 grams. So what do we expect over here? We expect 63.9 grams total. Not 63.9 grams of this or 63.9 grams of this, 63.9 grams total. Okay. All right. So D would be 13.6 grams plus 50.6 grams equals 63.9 grams of reactants, and therefore 63.9 grams of product. So if you did something like that, That would be perfectly fine. All right, so let's put that one off to the side. And let's see what this one is about. So this one is called a limiting reactant problem. So let me describe to you what a limiting reactant problem is using the idea of making bicycles. So let's say that you have a bicycle frame. So when you draw a bicycle frame, you draw a triangle and then another triangle attached to that. And you can see that we've got a nice bicycle frame going here. I'm going to put a little fork on it, and here's the handlebars. And if you want, you can put a little seat on it too. Now here's your bicycle frame. And to make your bike, you've actually got to put two wheels on it. So in this balanced reaction, one frame plus two wheels gives you one bicycle. So again, two triangles, draw your fork, your handlebars, and your seat. Now, when you draw the wheels on this, remember the wheels are centered at that little edge of the triangle and centered on that end of the fork. So there's your bicycle. You get one bicycle from one frame. You get one bicycle from two wheels. Okay. They teach this same thing. I saw a lecture at this at UC Davis, and they do the exact same thing for limiting reactant. Only the guy makes that his bicycle, and he makes that his wheel, and there's his bicycle. So this is College of the Redwoods, and this is UC Davis. I think you get more from College of the Redwoods. We teach you how to draw a bicycle. Okay, so let's take a look at this ratio. It's 1 to 2 to 1. So if we start off with 5 frames and we have excess wheels, excess means we have more wheels than we need. How many bikes are we going to get when we're done? And we're going to get 5 bikes because we've run out of frames. On the other hand, let's say we have excess frames and we have 10 wheels. How many bikes are we going to get? Well, you need 2 wheels per bike, so we're going to get 5 bikes here. Now, I'm going to change this number to 20, so here that we get 10 bikes. All right. So remember, excess frames, excess wheels. Now, suppose we don't know if we have excess wheels or excess frames. Suppose we have 5 frames and 20 wheels. How many bikes are we going to make? And the answer is 5. Why? Because after 5 bikes, you run out of frames. So in this case, this is called limiting, and this is called excess. And there are a couple of ways of figuring out whether or not you have which one of these is in excess and which one is limiting. One way to figure out which one is in excess and which one is limiting is you do this. You find out how much product you could make, and the answer is you make the smallest amount of product. So here, if we make 5, that means the frames are limiting. Okay, so here, let's take a look at this problem here and figure it out. Now, there is another way to figure out what is limiting. So for instance, we could start off with 5 frames and multiply by 2 bikes, or I should say 2 wheels per 1 frame, 2 wheels per 1 frame, and we get 10 wheels. So what does this mean? This means if you have 5 frames, you need 10 wheels. So in this case, if we have 5 frames, we need 10 wheels, which we have, and we have more than 10 wheels. Since we have more than 10 wheels, the wheels are in excess. So you might wonder, well, does this work if you start with 20 wheels? And it sure does. So you need 1 frame per 2 wheels, which means 10 frames. So 20 divided by 2 is 10. So this means that you need 10 frames for 20 wheels. We don't have enough frames for 20 wheels, but we have enough for 10. So again, that means that your frames are limiting and your wheels are in excess. Okay, so it doesn't matter which one of these two you start with to figure out which one is limiting and which one is in excess. Okay, so let's take a look at this problem here, and we're going to do a limiting reactant problem. So here I'm going to write calcium oxide and ammonium chloride makes ammonia, and H2O, you can't call that water because it's a gas, and calcium chloride. Now, we have 112 grams of calcium oxide and 224 grams of ammonium chloride. We want to find out which one is limiting. So we're going to do this two ways. We're going to take this, and you'll notice it says what mass of NH3 can be produced. I'm going to take my calcium oxide, turn that into moles of calcium oxide, turn that into moles of NH3, and then grams of NH3, and see what I get. I'm also going to take the 224 grams of NH4Cl, turn that into moles of NH4Cl, turn that into moles of ammonia, and then grams of ammonia. So we've done a number of these problems, and you should pause and do both of these problems and then hit play after you're done, because I'm going to kind of go through these pretty quickly. So make sure you pause, give yourself a chance to do this problem, get it right, and then see what I get here. Okay, so my molar mass of calcium oxide is going to be 40.08 plus 16. So that's 56.08 grams. For ammonia, it's 14.01 plus 3 of these, so that's going to be 17.04. And for NH4Cl, it's going to be 18.05 plus 35.45. So 1 mole of ammonium chloride is 30. Oh, that can't be right. $53.50. Okay, so I'm going to move this up here like this, and I'm going to do this very first one first. 112 grams of calcium oxide times 1 mole of calcium oxide per 56.08 grams of calcium oxide times 2 mole of ammonia to 1 mole of calcium oxide. You'll notice that when I'm doing this, I don't usually put the state down. I don't think that's necessary to identify the substance. And then we have 17.04 grams of ammonia to 1 mole of ammonia. I'm going to estimate 17 will go into that 3 times. 3 goes into 112 about 40 times, and 40 times 2 is 80. So it's going to be around 80, but a little less. And I get 68.1 grams of ammonia. And I estimated 80. My number's a little high. All right. Now the 224 grams of ammonium chloride times 1 mole of ammonium chloride per 53.50 grams of ammonium chloride times 2 mole of ammonia per 1 mole of, or 2 mole of ammonium chloride, and then times 17.04 grams of ammonia per 1 mole of ammonia. And here 17 goes into that almost 3 times. 2 divided by 2 is 1. So 3 goes into 224 about 80 times. So this is going to be a close race. Let's see what we have. 224 times 2 times 17.04 divided by 53.50 and divided by 2. And we get 71.3 grams of ammonia. So this one is the amount that we get. So this is our theoretical yield. And the reason we can't make this much is because we're going to run out of calcium oxide. So here, this one is if we use all of the calcium oxide, all of it. So this means that this is our limiting reagent or reactant. Limiting. So whichever one of these two that you start with gives you the smallest amount that you're limiting, and the other one is in excess. Okay, so we kind of tackled all of the problems at the same time here. We got the mass of ammonia, and we found out what was limiting and what was in excess. So that's one way to do it, and this is perfectly fine for that. Now, another way to do that is this. Take 112 grams of calcium oxide, convert that into moles of calcium oxide, convert that into moles of ammonium chloride, and convert that into grams of ammonium chloride. Because whatever number we get here, that's how many grams we need to react with 112. If this number is bigger than that number, then we have, I should say, if this number here that we calculate is smaller than that number, then yeah, we've got plenty to work with. But if the number we calculate here is bigger than this number, then we don't have enough of that. So that means not all of this will react, which means it's in excess. So we have 112 grams of calcium oxide. And this is one of those times where you want to pause it and then unpause it so that you don't have to write this down as notes, but rather you can learn from it by doing. So hit pause and then unpause. Okay, you're back. So 1 mole of calcium oxide per 56.08 grams of calcium oxide times 2 mole of ammonium chloride per 1 mole of calcium oxide, and then times our 53.50 grams of ammonium chloride per 1 mole of ammonium chloride. So when we multiply these numbers out, I would venture to guess that it's going to be about 224. So it's going to be really close. Actually, it's going to be a little smaller than 224 because 53.56 is bigger than 56.08. So I'm venturing that this answer here is going to be like 220. Okay, 112 times 2 times 53.50 and divided by 56.08. And we get 214 grams of ammonium chloride. So this is needed to react 112 grams of calcium oxide. We only have, I should say, not only have, we have 224 grams of ammonium chloride. So we have extra ammonium chloride. And when we have extra, what does that mean? Excess or limiting? Excess. And since all 112 grams of calcium oxide reacts, it is limiting. And there you go. Now, this answer here is not complete. What more do we need for this? Well, the question was, how much ammonia are you going to make? So that means for this answer to be complete, you would also have to have this written down below. Okay? So if you write this down below, then this would be a complete answer. So here we also get plus the conversion of 112 grams of calcium oxide to grams of ammonia. So if you take a look at this bottom one versus this top one, you're not really saving any calculation stuff. You're going to do two calculations regardless of which method you use. And so I kind of gravitate towards this one because the last two calculations here or the last calculation is identical, and they're very, very similar. And you just have to remember that the smaller amount tells you that that starting material was limiting, and the larger amount tells you that amount was in excess. And you're limiting, your amount that's smaller is your theoretical yield. Okay, we've done quite a bit today. I think we'll pick up with number 14 tomorrow. And thank you for listening.